let's continue to work on some sample problems in principles of hydrostatics. So here in this example, we have an oil which is flowing through the nozzle. As you can see here in the figure, we have a nozzle here, and the specific gravity of the oil is 0.7. It reflects the mercury in the U2 gauge. Here's the U2 gauge. Letter A, determine the value of H if the pressure at point A is 152 kilopascal. So here at point A, we have an existing pressure of 152 kilopascal. We are required to determine the deflection height of the mercury. So letter B, uh, we determine the pressure at point B, or the interface between the two liquids, okay, with the oil and the mercury. So let's start solving for the value of H. So recalling the general equation for pressure measurement, we have 2 points, point 1 and point 2. We have P2 minus P1, which is equals to, or this is the pressure difference, the sum of all the product of unit weight of the fluid and its corresponding height or deflection. So we have a sign convention that we have a positive sign for uh, downward direction, and we have a negative sign for sum of product of unit weight and H for upward. So depending on the direction of our reference point for the starting point of measuring the manometer, or measuring the pressure difference between uh, in the nozzle. So let's say here in this figure, we start, or our location of point 1 is at point A, and we will end measuring at point C. So this is the point 2. So we can rewrite this as PC, and here the point 2, and we subtract it by PA. Okay, so we determine the pressure difference between PC and PA. So since this is a type of manometer, um, we are required to just determine the gauge pressure. So if this is the free surface area at point C, so there's no pressure there. Okay, there's no pressure at point C, since that's the free water or free surface of the liquid. So at point A, it has a pressure because it is within the flowing fluid. So we solve now this using the sum of products of unit weight and height. So we have two liquids here. We have the oil. So if we start at point A, so our direction should be like this. Okay, from point A to point C. So starting at point A, uh, we take into consideration first the liquid, that is the oil. So we multiply the product, or we determine the product of the unit weight of oil and the corresponding height. So the corresponding height is the vertical distance from the starting point of the fluid to the end point of that fluid. So the end point is point B. So therefore, we have a vertical distance from point A to point B for the liquid, that is oil. So our total height is from point A to point B is 2.9 plus H. Next, let me replace this. That's 2.9 plus H. Then the next liquid to be considered is the mercury. So from point A to point B, then from point B going to point C. So from point B to point C, we have a difference in elevation from point B, the starting point of the mercury, and the end point of the mercury is at point C. So just take the difference in elevation between the two, which is H. So the direction here is upward. So earlier we have the oil, which is from point A to point B, that is going downward in direction. So this is positive. On the other hand, we have the mercury, which is from point B to point C, that's upward in direction. Therefore, we have a negative sign, which is the product of the unit weight of mercury multiplied by H. So this is our equation for this problem. We can now solve for H. So just substitute the given for pressure at point A, which is 152 kilopascal. That is equals to unit weight of oil. Unit of weight of oil is just the product of unit weight of water times the specific gravity of oil, which is given 0.7, multiplied by 2.9 plus H, minus unit weight of mercury, that's 13.6 in specific gravity. So specific gravity of mercury times H. Okay, so substitute now the other given. We have unit weight of water 9.81 kilonewtons per cubic meter. Specific gravity of oil 0.7 times 2.9 plus H, minus 9.81 kilonewtons per cubic meter times specific gravity of mercury 13.6 times H. Okay, let's simplify the equation by evaluating first the other terms. Pascal, that is equals to, we multiply first 9.81 by 0.7. So 9.81 times 0.7, 6.867. 6.867. The unit is still kilonewtons per cubic meter. 2.9 is in meters plus H, minus 9.81 times 13.6, 133.416. That is still in kilonewtons per cubic meter, but we multiply it by H. So 133.416 H in kilonewtons per cubic meter. Okay, so let's distribute 6.867. We have 2.9 times 6.867 is equals to 19.9143. 19.9143. So unit will be kilonewton per square meter. Then multiply again 6.867 to each. Just multiply by H, unit kilonewtons per cubic meter. Minus, we have 133.416 each kilonewtons per meter. Combine like terms. Okay, we have terms here that has H variable, and we have full numbers here. So we combine now like terms. Uh, Negative 152 kilopascal transpose 19 becomes negative 19.9143. That's in kilopascal. And we add 6.867 to negative 133.416. So 6.867 minus 133.416, that's negative 126.549 H. Okay, kilonewtons per cubic meters. Subtract negative 152 by 19.9143. Negative 171.9143 equals to negative 126.549 kilonewtons per cubic meter to be multiplied by H. So to determine H, divide both sides by its coefficient, which is 126, negative 126.549, which is kilonewtons per cubic meter. So this is in kilopascal. Kilopascal is kilonewtons per square meter. So negative 126.549 kilonewtons per cubic meters. So this will be cancelled out. We will have an answer that is positive. So, negative 171.9143 divided by negative 126.549. The answer is 1.358. So kilopascal divided by kilonewtons per cubic meter, or kilopascal is in kilonewton per square meter. So that will be cancelled out, and what unit remains is meter. So the answer is 1.358. Can rewrite this as H equals 1.358 meters. Okay. Letter B. For letter B, what is the pressure at point B? Okay, what's the pressure at point B? So from point A to point B only. So from point A to point B, we can determine the pressure at point B. So let me rewrite here. Pressure difference general equation. If our endpoint is at point P, we have PB minus PA equals to the sum of the product of unit weight and height. Since we have just one fluid that is concerned here, that is oil only up to point P. So we only have one, that is positive product of unit weight of oil times TH. Okay, the height there is 2.9 plus H. 2.9 plus H, because that's the interface or the height from point A to point B. So that's all contained with oil from point A to point B. So point A is pressure at point A is given, point B unknown. So let's rewrite the equation. Uh, P transpose pressure A to the right hand side of the equation, we have becomes positive. So PA as unit weight of oil is 2.9 plus H. So pressure at B is equals to pressure at A given 152 kilopascal. So positive 152 kilopascal, or kilopascal is kilonewton per square meter. So that's the same. Plus unit weight of oil 9.81 kilonewtons per cubic meter multiplied by the total height 2.9 meters plus the computed H 1.358. 1.358 meters. So the pressure B is equals to. Okay, let's evaluate first the second term. Let's add first 2.9 by 1.358. 4.25. So 152 kilonewtons per square meter plus 9.81 kilonewtons per cubic meter is multiplied by 4.258 meters. So meter is cancelled out. We have kilonewtons per square meter unit. So pressure at B is equals to, we can directly solve this, 152 plus 9.81 times 4.258. So the answer for pressure at point B is 193.771 kilopascal. So that's the answer. Okay, that's the answer. So again, the sign that we use for the product of unit weight and height for oil is positive because from point A to point B, that is downward direction, so that's positive. That's the answer for this problem. Next, for the manometer shown, determine the pressure at the center of the pipe. Center of the pipe, here's the pipe. The center is located here. Okay, so let's apply again the solution for pressure difference. So let's say we start at the center of the pipe. Let that be point 1. Okay, we assign this as point 1. The endpoint is at the free surface of the mercury. That's the endpoint. So we end there, point 2. So the direction is from point 1 going to point 2. So we have two liquids here. General solution, we have pressure difference P2 minus P1 is equals to the sum of the products of the unit weight and its height, or its difference in elevation of that particular liquid. So we have plus or minus sum of product of unit weight times H. So we're required to determine the pressure at point 1. So point 2 is at the free water surface, or at the free surface of the mercury. So there's no pressure present at point 2. So that's 0. So what remains is pressure 1. Negative P1 is equals to plus or minus sum of gamma H. So starting at point 1, considering this liquid that is oil. So we start at point 1 and the oil ends at this point. So this is the interface between the oil and the mercury. So determining, or based on the figure, we have a difference in elevation from the center of the pipe to that point, which is 1.7. So the direction is from point 1 to the end point. Okay, means the difference in elevation is going up from this point to that point. So we have a negative sign for the product of unit weight of oil and the H, which is 1.7 meters. The next one is the mercury. Mercury start at this point and end at that point. So we have a vertical distance of 1 meter and the direction is going upward, start from start to end. So going up is also negative. So negative unit weight of mercury times H, which is 1 meter. Okay, So negative P1 equals to negative 9.81 kilonewtons per cubic meter or unit weight of water multiplied by the specific gravity of the oil, which is 0.8 times 1.7 meters minus 9.81 kilonewtons per cubic meters multiplied by specific gravity of mercury, 13.6 times 1 meter. So the units that we will have are in kilopascal, which is kilonewtons per square meter. So let's calculate first. 9.81 times 0.8 times 1.7. It's negative 13.3416 kilopascal minus, this is 13.6 times 1, negative 133.416. So negative P1 negative 13.3416 minus 133.416 negative 146.7576 kilopascal. Okay, so let's make P1 positive. We multiply both sides by negative 1. So P1, pressure at point 1, is equals to positive 146.7576 kilopascals. So that's the answer for the pressure in the pipe. So that's how manometer works. We just determine the pressure differences or just determine the pressure head of each liquid, and through those pressure head using this general equation we can determine the pressure at the pipe. Okay, problem number 3. A closed tank contains 2 meters of water, 4 meters of oil, and the air above the oil has a pressure of 40 kilopascal. If an open mercury manometer right here at the bottom of the tank has 1 meter of water, determine the deflection Y of mercury. Okay, so we have three fluids here. We have oil, water, and mercury. And above the oil, we have air, which has a given pressure of 40 kilopascal. So let's solve this using the general equation that is the pressure difference equals to the sum of the product unit weight and H for each liquid. So our starting point is at point 1, and point is at point 4. So point 1, uh, we have a pressure difference of P4 minus P1 equals to the sum of products unit weight and H. So at P1, uh, it was supposed to be a free surface of oil. But since we have pressure of air above point 1, it means the pressure at point 1 is also the pressure of the air. So P1 is equals to 40 kilopascal. So P4 minus 40 kilopascal. So that's the pressure at point 1 because the only contributing pressure there above point 1 is the pressure of due to air. Next, it is equals to the first fluid is the oil. So from point 1 to point 2. So the direction from point 1 to point 4 is from here going to point 4. So from point 1 to point 2, that is downward. Downward, therefore we have a positive sign for the product of the unit weight of oil and the h, which is 4 meters, the height of oil. Okay, from point 1 to point 2. Then the next liquid that we have is water. So it started from point 2 and ended at point 3. So from the bottom of the tank, it extended to the manometer by 1 meter. So also it is going downward. So from point 2 to point 3, that's positive unit weight of water times the total height of the fluid. So starting from the interface between the oil and water, that is at point 2, and we end at point 3. So total height is 3 meters. Then the third fluid is the mercury. So starting at point 3 to point 4. So point 4 is above point 3. So it means we have upward direction. So that's negative. Negative unit weight of mercury times h, which is y, the deflection of mercury. So we put y here. So pressure at point 4, so that's the free surface of the mercury. So it has no pressure there. So there's no external pressure present above point 4. So that's equals to 0. Since we're concerned here with gauge pressure. So this is 0. Okay. Negative 40 kilopascal is equals to unit weight of oil 9.81 kilonewtons per cubic meter. That's the unit weight of water multiplied by specific gravity of oil, which is 0.82 in order to have a unit weight of oil, times 4 meters plus 9.81 kilonewtons per cubic meter times 3 meters minus 9.81 kilonewtons per cubic meter times 13.6 specific gravity times y. Okay, so let's evaluate. Let's multiply 9.81 times 0.82 times 4, 32.1768. So kilonewton per square meter is kilopascal plus 9.81 times 3, 29.43 kilopascal minus 9.81 times 13.6 is 133.416, still in kilonewtons. So y is in kilonewtons per cubic meter unit. Okay, so combine like terms. Okay, we can move these terms to the other side of the equation. So we'll have negative 32.1768, have negative 29.43 kilopascal equals to negative 133.416 kilonewtons per cubic meter times y. Okay, so negative 40 minus 32.1768 minus 29.43. So negative 101.6068 kilopascal equals to negative 133.416 kilonewtons per cubic meter times y. Okay, So divide both sides. So let me rewrite this equation. Kilopascal is in kilonewtons per square meter. So divide both sides by negative 133.416 kilonewtons per cubic meter, negative 133.416 kilonewtons per cubic meter. So we cancel out. Okay. And the unit remains is in meters. So y is in meter. Uh, B divided by 101.6068 divide negative 133.416. So that's positive 0.76157 or 16 meters. So that's the height. Okay, that's the distance y, vertical distance y. Okay, y equals to 0.7616 meters. Last problem. Closed compartment shown contains water 3 meters deep at the left side and 5 meters deep on the right side. If the pressure at point A, so our point A here is, say at this point, is 98 kilopascal, it is an absolute pressure on the closed compartment shown, which we have a given specific weight of air, which is 0.012 kilonewtons per cubic meter. What is the absolute pressure at point B, so on the other side, considering the specific weight of the air? For letter D, if we will neglect the specific weight of air, what will be the absolute pressure at point B? So since class this is a closed compartment, so uh, the fluids or the pressures inside this compartment is not affected by the atmospheric pressure. So since it is closed, um, atmospheric pressure will not affect the value for our gauge pressure at point A and point B. So since this is closed, let's just compute the gauge pressure on each point, from point A to point B. So let's just compute the gauge pressure, and that will also be your absolute pressure since this is a closed container. Okay, so what is the absolute pressure at point B considering the specific weight of air? So this is point A, point B. So let's determine the pressure difference from point A to point B. That is equals to the sum of the product of pressures of, or sum of the product of unit weight of each fluid multiplied by its height. So starting at point A, um, we have a fluid here that is the air. We consider the air. So we're starting from the top to the surface of water on the left side. So we have a distance of 5 meters. So from the top to the surface, that is going downward. So it means that is positive. So we have positive unit weight of air, sorry, air is multiplied by its height, which is 5 meters. Next is we have the fluid that is water. So if we start here and we end there, okay, it means that it is going upward, starting from this point to that point. Since our direction is from point A going to point B. So it's going upward. What is the vertical distance between the surfaces of water on the left and right side? So we have 5 meters here. have 3 meters, just subtract them, we have 2 meters. So the water is going upward, that's negative. Negative unit weight of water times 2 meters. And the last fluid is again air. So from the interface between the water and the air going to point B, so we have upward direction and the distance is 3 meters. So it is upward negative. So negative unit weight of air times 3 meters. Okay. So what is required is pressure at B. So pressure at A is given, which is 98 kilopascal. So we move that to the right hand side of the equation, we will have a positive pressure of A, which is 98 kilopascal. So I just move pressure A becomes positive here, and substituting the given, we have 98. So unit weight of air given 0.012 kilonewtons per cubic meter times 5 meters minus 9.81 kilonewtons per cubic meter times 2 meters minus unit weight of air 0.012 kilonewtons per cubic meter times 3 meters. So the pressure at point P is 98 kilopascal plus 0.012 times 5, 0.06 kilopascal minus 9.81 times 2, 19.62 kilopascal minus 0.012 times 3, 0.036 kilopascal. Okay, combine like terms. So just add them all. 98 plus 0.06 minus 19.62 minus 0.036. So the answer is positive 78.404 kilopascal. That's your answer for the pressure at point P. Okay. So for letter B, we neglect the pressure of air. Okay, just neglect. There's no contributing pressure due to air. So what we will do here is using the same solution, only that using the same solution, we will neglect air. Okay, so this will be removed. So it goes without air. Okay, this will be removed. This one, so one can easily determine pressure at B, which is 98 kilopascal minus 9.81 kilonewtons per cubic meter times 2 meters. So pressure at B is 98 kilopascal minus 19.62 kilopascal. So the pressure at point B is 98 minus 19.62, 78.38 kilopascal. That's the answer for letter D. Okay, so that's it. That ends our lecture for hydrostatics. Thank you for watching. God bless.